ME204, Coefficient of Restitution, Line of Impact, and Plane of Contact. So far, we've seen collisions where the objects stick together and we have one final mass after the impact. What happens when we have two objects that bounce off of each other? That's what we want to talk about today. In the bottom left corner of the screen is an example of a central impact. Both quarters have velocities in the same line of action, and after the collision, the velocities stay in that same line of action, for example, in the x direction. The BBs on the right, when they collide, hit at an angle, and we have what's called an oblique impact. We're also going to talk about the difference between an elastic impact and a plastic impact. All other collisions fall between these two limits. First of all, let's review what happens with objects that collide and become one. Here we have a ball A that has a mass of 3 kilograms. It's moving at 5 meters per second. And ball B has a mass of 2 kilograms and is moving at 4 meters per second to the left. If the balls stick together upon impact, how fast and in which direction will they be moving after the impact? Well, we can look at the momentum before and set that equal to the momentum after to solve this problem. Before, we have 3 kilograms times 5 meters per second plus 2 kilograms times a minus 4 meters per second, which equals our final mass, the combined mass, 3 plus 2, times our final velocity. We have one unknown and one equation, so we can easily solve this to find that our final velocity is 1.4 meters per second to the right. But what if they don't stick together? We have the same problem, the same masses, the same velocities, and we want to know how fast and in which direction each ball is going to be moving after impact. After we have a collision, if they don't stick together, they bounce off of each other, and we have velocities in opposite directions. So we can look at our momentum before and our momentum after like we did in the previous problem, but when we do this, notice that since our masses don't combine, we have two separate unknown velocities on the right side of the equation. So there are two unknowns and only one equation. We need another relationship in order to solve this problem. If before I have a ball A that's going 4 meters per second and a ball B that's going 6 meters per second, then the approach velocity of these two objects is 10 meters per second. It's like saying that the velocity of B relative to A's perspective is 10 meters per second. After the collision, B is going 5 meters per second and A is going 3 meters per second, and they're going in opposite directions, so their separation velocity is 8 meters per second. Again, this is like saying that the velocity of B from A's perspective is 8 meters per second. If we look at the separation velocity with respect to the approach velocity, it'll give us a percentage of how much velocity we still have after the collision. This is what we call restitution. So our separation velocity is 8 meters per second, and our approach velocity is 10 meters per second, so we have a restitution of 80%. Remember our school bus example? We've talked about this several times. If the bus is traveling 55 miles an hour and a boy is running down the aisle at 5 miles an hour, we have a relative velocity of the boy running down the middle of the bus of 5 miles per hour, but how fast is the boy actually moving? He's moving 60 miles an hour. And we can write an equation for what we would do intuitively to find that 60 miles an hour. If we call the bus A and the boy B, then the velocity of B, the boy, is equal to the velocity of A, the bus, plus the velocity of the boy from the perspective of the bus, or relative to the bus. We can rearrange the equation so that it looks like the velocity of the boy with respect to the bus is equal to the velocity of the boy minus the velocity of the bus. Now let's look at restitution and see if we can come up with an equation for a coefficient of restitution. Well, we said that our restitution is a separation velocity to an approach velocity. We also mentioned that our separation velocity is a relative velocity, and our approach velocity is also a relative velocity. So if we write our separation velocity as the final velocity of B with respect to A, and our approach velocity as the initial velocity of B with respect to A, and knowing that the approach velocity is a positive value, the separation velocity would then be negative since they are separating and moving in opposite directions. So let's put a negative sign in front of this ratio to force the overall answer to be positive. Then if we write the equations for relative motion, then our separation velocity becomes the final velocity of b minus the final velocity of a, divided by the initial velocity of b minus the initial velocity of a. Carrying our negative sign through the denominator, we rearrange the equation to get that our coefficient of restitution is equal to the final velocity of b minus the final velocity of a, divided by the initial velocity of a minus the initial velocity of b. The distribution of the negative sign causes the order of the variables in the denominator to be switched. Note that our coefficient of restitution is always a positive value. The coefficient of restitution really measures the bounciness of the objects that are colliding. Let's look at some special cases. What if we have a coefficient of restitution of 0? In this case, our separation velocity must be 0, which means that they're not separating from each other at all. Objects that collide and stick together behave in this way. This is what we call a perfectly plastic collision. Although momentum is conserved, the maximum amount of energy is lost in this type of collision. Now what if we have a coefficient of restitution of 1? Well, this would mean that the separation velocities are the same as the approach velocities. Objects that bounce off each other with 100% of the relative velocity restored exhibit this kind of behavior. This is a perfectly elastic collision. Momentum is, of course, conserved, and zero energy is lost in this type of collision. Note that this represents a limit to our coefficient of restitution and is not realistically possible. Now we have two equations to help us find the two unknown velocities in our previous example. We have conservation of momentum, and we have our coefficient of restitution, which is equal to our separation velocity divided by our approach velocity. Let's go back to our example. We wanted to know how fast and in which direction each ball was moving after impact. Let's say our coefficient of restitution is 70% for this example. To find our separation velocity, or the velocity of each object after the collision, we'd start with our first equation, which would be our momentum equation, and knowing that momentum is conserved, we can write out that equation as we did previously and have our same two unknowns, our velocity of A and our velocity of B, in the final condition. Again, two unknowns, so we need a second equation. In this case, we'll use our coefficient of restitution, which is 0.7. That will be equal to the velocity of B after the collision minus the velocity of A after the collision, divided by the initial velocity of A, which is 5 meters per second to the right, minus the velocity of B, which is 4 meters per second to the left, and so it's negative. Now we have the same two unknowns in our second equation and can solve the two equations simultaneously to obtain our velocities. In this case, the velocity of A after the collision would be minus 1.12 meters per second, and the velocity of B after the collision will be 5.18 meters per second. Now what if the objects don't collide head-on? In this case, we have to define a plane of contact and a line of impact. For two circular objects, when they collide, there's one point of collision. If we draw a line tangent to each circle, that defines our plane of contact. A line perpendicular to the plane of contact will give us our line of impact. If we then break these velocities into components along the line of impact and the plane of contact, so for the quarters case we have 4 along the line of impact and 3 on the plane of contact, and for the penny we have 6.4 along the line of impact and 4.8 along the plane of contact, then we can better evaluate what's happening to these objects when they collide. These components are going to change during the impact. Notice that when we draw these at the center of gravity, that the components that lie along the line of impact, if they were allowed to continue forward, they would collide with each other. However, the components that are along the plane of contact never change. They stay the same. If we draw these again at the center of mass and allow them to continue, They pass by each other and don't influence each other, so these components stay the same. Momentum is, of course, conserved in all directions. The coefficient of restitution will only apply to the components of velocity in the line of impact. We need to also look at what happens with collision with stationary objects. For example, what happens when a ball bounces on the ground? Well, we have a velocity of the ball when it hits the ground, and that can be broken into components. We'll use a green arrow to denote the collision along the plane of contact and a red arrow to denote the collision along the line of impact. In the x direction, which is along the plane of contact, the velocities don't change. So the velocity of the ball in the x direction initially is equal to the velocity of the ball in the x direction finally. For the y direction, or along the line of impact, we would use our coefficient of restitution to solve this problem. This would be defined by the final velocity of the ball in the y direction minus the final velocity of the ground in the y direction divided by the initial velocity of the ground in the y direction minus the initial velocity of the ball in the y direction. However, the velocity of the ground is equal to 0, so we can cancel those out of our equation immediately. That leaves us with a coefficient of restitution equal to the final velocity of the ball in the y direction divided by the initial velocity of the ball in the y direction. And note that we have a negative sign here, which means that our velocity changes directions. Now that we have the y and x components of our velocity, we can find the magnitude and the direction of that velocity when an object bounces off the ground or any other stationary object. Let's look at an example of an oblique impact. We have a quarter that has a mass of 5.67 grams and is moving at 5 meters per second. The penny has a mass of 2.5 grams and is moving at 8 meters per second. The plane of contact is at 48 degrees from the horizontal. How fast and in which direction is each coin moving after impact? Let's assume that we have a coefficient of restitution of 75%. There's my plane of contact at 48 degrees. My line of impact will be perpendicular to that plane. Next, we break our velocities into components in the x direction and the y direction. Solving for these components, for the quarter, in the x direction, we would have 5 times the cosine of 48 degrees, which is equal to 3.35 meters per second. In the y direction, we have 5 times the sine of 48 degrees, which is equal to 3.72 meters per second. For the penny, in the x direction, 8 cosine of 48 degrees is equal to 5.35 meters per second. And 8 sine of 48 degrees is equal to 5.95 meters per second in the y direction, or along the line of impact. Now that we have the components, we can move towards solving for what happens after the collision. Along the plane of contact, the velocities don't change, so in the x direction, the final velocity of the quarter in the x direction is equal to 3.35 meters per second, and the final velocity of the penny in the x direction is equal to negative 5.35 meters per second. Along the line of impact, the velocities do change. We'll need a couple of equations. Our first equation will be our momentum equation. The mass of the quarter times the initial velocity of the quarter, plus the mass of the penny times the initial velocity of the penny, is equal to the mass of the quarter times the final velocity of the quarter, plus the mass of the penny times the final velocity of the penny, all in the y direction, or along the line of impact. Filling in what we know leaves us one equation with 2 unknowns. So we need another equation. We'll use, for equation 2, the coefficient of restitution. Filling in the denominator with the initial velocities that are known in the y direction, we have our second equation with our 2 unknowns, knowing that our coefficient of restitution is equal to 0.75. Solving both equations for our final velocity in the y direction of both the quarter and the penny gives us that the final velocity in the y direction of the quarter is 1.46 meters per second, and the final velocity of the penny in the y direction is equal to negative 5.79 meters per second. Knowing the components, we can now solve for the magnitude of the final velocities. The magnitude of the velocity for the quarter becomes the square root of 3.35 squared plus 1.46 squared, which is equal to 3.65 meters per second. We use geometry and trigonometry to determine what the angle is from horizontal of that velocity. The angle from horizontal becomes 48 degrees plus the inverse tangent of 1.46 divided by 3.35, or 71.5 degrees from the horizontal. For the penny, if we draw its components in, then we can find the magnitude of the velocity of the penny after the collision. The magnitude of the velocity of the penny becomes the square root of negative 5.35 squared plus negative 5.79 squared, which is equal to 7.89 meters per second. Again, we'll use geometry and trigonometry to determine the angle of that velocity from the horizontal. The angle from horizontal becomes 180 degrees minus 48 degrees plus the inverse tangent of 5.79 divided by 5.35, which gives us 84.7 degrees. So we have a final velocity of the quarter of 3.65 meters per second at an angle of 71.5 degrees. The penny has a velocity of 7.89 meters per second with an angle from horizontal of 84.7 degrees. Our next topic is particle kinetics using angular impulse, angular momentum, and conservation of angular momentum.